So for AP problem number 7, part A asks us, under standard conditions at 25 degrees Celsius, zinc reacts with cobalt to produce, when it reacts with cobalt, the aqueous solution, with cobalt, the solid. So for part I, it asks to write a balance equation for the oxidation half reaction. So if we look at the fact that zinc combines with cobalt plus 2 in the question, and it produces cobalt 0. So we know that cobalt is being reduced and that zinc is being oxidized. So if we look into our book, we can find that originally zinc is being oxidized in the equation in the book, so we flip it and it'll give us this equation. Zn turns into Zn plus 2 electrons, and this is the energy that it produces. And for part 2, it asks us to write a balanced net ionic equation for the overall reaction. So normally we would have this, but it'd be the other way around. So we had to flip it because it was on the wrong side. And we have cobalt plus 2 electrons turns into cobalt. And since we have our electrons on opposite sides, we can cancel those out. And it'll give us Zn plus Co plus 2 turns into Zn plus 2 plus Co. For part 3, it asks us to find the energy, and the energy for the flipped reaction for zinc is 0.76 volts, and the energy for cobalt is negative 0.28 volts. And when we add those together, it'll give us 0.48 volts. So for part B, at 25 degrees Celsius, H2O2 decomposes into the given equation. And the given equation's energy is 0.55 volts. For part 1, it asks us to determine the value of the standard free energy change, that delta G for reaction 25 degrees at 25 degrees Celsius. So we're going to plug it into this equation. Delta G equals negative NFE 0. So negative 2 is our moles. 1 Faraday is 96,500 right here. And then our energy is 0.55. And that'll give us, if we plug that into the calculator, it'll give us negative 1.1 times 10 to the 5th joules. For part 2, we have to plug it into this equation. Delta G equals negative RT and initial K. And we know that for delta G, it's negative 1.1 times 10 to the 5th. So we have that part equals this constant right here. And this is the temperature, so we have to find K. So if we put that into our calculator, we'll find that K equals 2.0 times 10 to the 14th. And for part 3, it says the standard reduction potential, E, for the half reaction O2 plus 4H plus 4 electrons turns into 2H2O. And that has a value of 1.23 volts. Using this information, in addition to the information given above, determine the value of the standard reduction potential of E for all the half reactions. For the half reaction that's below, which is O2 plus 2H2 plus 2 electrons turns into H2O2. So we're going to combine the two equations that are given to us, and we have to flip. No, scratch that. We have these equations. The electrons are on opposite sides, so we have that. We cancel out the electrons, and that gives us this equation right here. and we'll just divide by the common denominator and add the energies together, which will give us 0.68 volts. And if we divide by the common denominator, we'll have O2 plus 2H plus 2 electrons turns into H2O2. And since changing the values of the moles doesn't affect the energy, it'll remain the same as 0.68 volts. So part C says, in an electrolytic cell, copper is produced by the electrolysis of CuSO4. It also says calculate the maximum mass of copper that can be deposited by a direct current of 100 amperes pass through 5 liters of 2 molality of CuSO4 for a period of 1 hour. So we have to take 1 hour, convert it to minutes, then seconds, then convert seconds into C, and then convert C into moles, and the moles into copper, and the moles of electrons, and electrons into copper, and then copper into grams. And then we plug all of that into the calculator, and that'll give us 119 grams of copper.